Well, good afternoon, everyone. Thanks for joining us today. My name is Rogelio Sullivan, and this is the monthly Power America technical webinar on wide bandgap power electronics. We do this on the first Wednesday of each month at noon, and today we have the pleasure of hearing from Gilbert Moreno from the National Renewable Energy Lab. Next month, on Wednesday, December 4th, we'll hear from the Naval Research Laboratory. But today it's NREL's turn. And what I'll do is just have a brief introduction for Gilbert, and then he'll talk for about 30 minutes. And then after that, we have plenty of time for Q&A. But what I'd ask you to do is to use the chat function at the top of the WebEx toolbar and type your questions in that chat function. You can type the questions in from the very beginning. And then as soon as Gilbert is finished talking, I'll read the questions out so that everyone can hear them clearly, and he will answer them. That way we won't be just trying to talk over each other. So with that, I will introduce Gilbert. Gilbert Moreno is a senior engineer at the National Renewable Energy Laboratory, where he conducts research into the thermal management of automotive power electronics. He's worked at NREL for over 10 years, developing advanced cooling technologies for various Department of Energy and industry-funded projects. Gilbert received his BS in Mechanical Engineering from the University of Texas at El Paso, and his MS and PhD degrees in Mechanical Engineering for the University of Texas at Arlington. And with that, Gilbert, I'll turn the full mic over to you.
Okay, thank you, Rogelio. Hopefully everyone can hear me okay. Today I'll present NREL's recent work to develop thermal management strategies for wide bandgap power electronics. Before I begin, I want to acknowledge the team members that have contributed to this project and are listed on this slide here. And so some of the work that I'm going to be presenting was actually done by some of these co-workers, and so if there are any questions related to that work, I can do my best to answer that, but in some cases I may not know the answer, but I could get back to you. Okay, so I work within the Advanced Power Electronics and Electric Motors Group at NREL, or APEM Group for short, and so this slide summarizes the research focus areas for our group. And so power electronics thermal management research is focused on developing advanced cooling technologies for power electronics. And so we've looked at anything from air cooling to liquid cooling and two-phase cooling. Advanced packaging designs and reliability research is focused on evaluating the reliability of electrical interconnects and also bonded interfaces, really with a focus on high temperature wide bandgap devices. And then electric motor thermal management research is focused on measuring the thermal properties of motor components and also evaluating different convective cooling technologies, including the use of transmission fluid as a coolant. Management research. And so this work is part of the DOE VTO funded project that's aimed at developing advanced cooling technologies for automotive power electronics. And so most of my presentation will be focused on this. So first I'll give a quick background of current automotive power electronic cooling systems, and then I'll state the project objectives and the approach. I'll describe our work to design a cooling system, and then finally I'll discuss our experimental demonstration work that is currently in progress. The second part of my presentation will be related to our gallium oxide device research. And so this work is part of an NREL LDRD funded project, and that's aimed at developing the next generation ultra wide bandgap devices. So I'll give a quick background, then I'll describe the results of a techno-economic analysis, and then I'll show some TCAD modeling results for some promising device architectures. And so first I'll talk about our power electronics thermal management research. So this is a quick background, basically showing the current ways that automotive power electronics are being cooled. And so older systems used a cold plate cooled configuration, which you see on the left. So in this case, you had the power module that was mounted onto a cold plate with thermal grease at the interface. And so the thermal grease in these systems was the largest thermal resistance. And for that reason, the thermal performance of these systems wasn't typically very good. And so more modern systems are using a base plate cooled configuration, which I'm showing there in the middle. And so this case eliminates the cold plate and directly cools the bottom of the base plate. And so this approach eliminates the thermal grease, which is a big thermal resistance. And because of that, you get better performance with this as compared to the cold plate cooled design. So advances in packaging and electrical interconnects have allowed for double-side cooled modules, and that's what you see on the right-hand side. And so in this approach, the power module is cooled on both sides through cold plates. And so by doubling the cooled surface area, you get better performance with these packages as compared to the other two. And so the bottom kind of shows the trend of what we're seeing for automotive applications. And so this slide summarizes the various thermal resistances within a base plate cooled configuration. And so these results are for the 2014 Honda Accord hybrid. And so on the graph there, I am plotting the temperature profile from the device all the way to the fluid. And so you can see the temperature drops to various layers of the package, including the device solder, the ceramic, the substrate solder, and then also the convective resistance. And so from these modeling results, we estimate that the package, or the conduction resistance, is about 70% of the total thermal resistance. And so that's the resistance from the device all the way to the bottom of the base plate. The convective resistance, which is from the bottom of the base plate to the fluid, only accounts for about 30%. And within the package, the ceramic typically makes up the largest thermal resistance. And so one way of improving the thermal performance is by reducing that conduction resistance through elimination of some of these package layers. And in today's presentation, I'll talk about a cooling strategy that we're looking at that allows for removing of the ceramic layer by using a dielectric fluid to cool the module. Okay, so the reason we're conducting this research is because thermal management is essential to increase the power density and the reliability in all electronic systems. And so the specific objective for this project is we're trying to develop thermal management techniques to enable achieving the year 2025 Department of Energy's power density target of 100 kilowatts per liter. And so using wide bandgap devices enable us to achieve this target because they are more efficient, they can operate at higher temperatures. The challenge is to create thermal solutions that allow for packaging of high temperature, wide bandgap power electronics in close proximity to capacitors that typically cannot exceed about 100 degrees C. Although there are advances to capacitors that's pushing that temperature limit. Automotive applications typically about 100 degrees C. And so this is the approach to develop a thermal strategy to reach a power density of 100 kilowatts per liter. And so first what we did is to define a thermal target that would allow us to reach that power density. And that thermal target was defined in terms of a volumetric thermal resistance, where the thermal resistance was scaled by the volume requirements for the power module and the cold plate. In this case, the thermal resistance was computed by first estimating the heat load of a 100 kilowatt wide bandgap inverter, which we estimate to be about 2,150 watts. Then assuming high temperature wide bandgap devices, we assumed a maximum junction temperature of 250 degrees C and a cooling temperature of 65. And then we did some analysis, and we estimate that the power module and the cold plate volume needs to be less than 240 milliliters. And that's in order for all the other components to fit within that 1 liter volume. So essentially we're trying to do 100 kilowatts off of 1 liter volume inverter. And so this resulted in a volumetric thermal resistance target of 21 centimeters cubed degrees per watt. And so the next step was to design the cooling strategy that would allow us to reach that thermal resistance target. And so this was done through modeling, where we compared the performance of different device packaging configurations And so we looked at more conventional packaging configurations. They used DVCs. We also looked at more advanced cooling configurations. And then for each packaging configuration, we evaluated the effect of the convective cooling performance. And we did this by varying the range of heat transfer coefficients. And by varying the heat transfer coefficients, we're also evaluating the effect of different fluids, like air, water, ethylene glycol, and refrigerants. Sorry about that. So this led us to pursue a dielectric fluid concept that I'll talk about on the next slide. This slide describes the dielectric fluid. Sorry. The dielectric cooling concept. So essentially, the concept uses a planar package where you have a MOSFET that's placed between two electrically conductive plates. The top plate is both an electrical conductor and also a heat spreader. And so we have a dielectric fluid that's impinging on the top surface of that external plate. And so the fluid doesn't directly contact the device. And the heat is being removed through single-phase heat transfer. We do need a dielectric fluid because the fluid is in direct contact with electrically active surfaces. A benefit of this cooling approach is that we can cool the electrical connections by simply flowing dielectric fluid over them. In our past work, we've shown that cooling the electrical connections is the best way of reducing the capacitor and the gate driver temperatures. And that's because these connections are the primary heat flow path from the devices to the capacitors and to the gate drivers. Another benefit of this cooling approach is that you can eliminate the expensive ceramics that are typical for DVC-based packages. And so if you look at the schematic here, the dielectric material that's shown on the bottom is not in the heat flow path because the heat flows upwards towards the fluid. And because of that, the dielectric material does not need to be thermally conductive. It can be made out of something that is inexpensive. And so there's that added benefit of using a dielectric fluid. And so there are various dielectric fluids that are available. In this case, we selected two synthetic hydrocarbons that are currently used in electronics cooling single-phase applications. So one is Alpha-6, and that's made by a company called DSI Ventures. And most of the modeling work that I'm going to be showing was done using this fluid. And the reason we use this fluid is because it has a high flash point of 246. And that is ideal considering we're targeting a maximum junction temperature of up to 250 degrees C. The other fluid was AmpCool or AC100, and that's made by a company called Engineered Fluids. So this fluid is designed for cooling of batteries and electric motors in EV vehicles. And so because it's intended for EVs, it makes sense to consider it for this case. There's also the potential to use automatic transmission fluid, or ATF, because this can decrease the cost. It can allow for the use of a fluid that's already qualified for automotive use. And it could potentially enable integrating the inverter with the motor. The reason we haven't looked at ATF at this point is because we're unsure on its dielectric fluid properties. But we have been in communication with some of the companies that manufacture ATF, just trying to see if we can better understand its properties. And so the table below compares the properties of the two dielectrics with that of ATF. And then I'm also showing the properties of water ethylene glycol, or WEG, for comparison. And so as you can see, the two dielectrics have properties that are very similar to ATF. They have slightly lower viscosity, and that's a good thing. The downside of these dielectrics is their poor properties as compared to water ethylene glycol. So for example, water ethylene glycol has a thermal conductivity that's about 3 times higher than that of the dielectric fluids. Also, the dielectric fluids have higher viscosities, which can result in higher pumping power. And so one of the challenges here was to create a cooling system with high thermal performance using fluids with relatively poor thermal properties as compared to WEG, which is the conventional coolant in automotive electronics. So this slide describes the cooling system design to cool one device. And so we did a lot of modeling work to optimize the size of the slot jet and also of the fins. And so the final design used a slot jet with dimensions of 1.75 millimeters by 10 millimeters. And so that jet impinged on fins that were 0.2 millimeters in thickness, 4 millimeters in height, and 10 millimeters in length. And so that design achieved an overall heat transfer coefficient of about 17,300 watts per meter squared degree K at a relatively low jet velocity of about 0.3 meters per second. And so this is a relatively high performance considering we're using a fluid with relatively poor properties. And higher performance is possible. We predict that we can achieve heat transfer coefficients greater than 35,000 watts per meter squared degree K using higher fin densities and at higher jet velocities. However, we picked this design because it minimized pumping power, but it also achieved a relatively high level of performance. So with the design, we predict that we can dissipate the 2.2 kilowatts of heat with only 12 devices. And so that results in a heat flux per device of about 718 watts per centimeter squared and the maximum junction temperature of 220 degrees C. And so it's the ability of the system to dissipate a large amount of heat that allows us to reduce the number of devices to decrease the overall volume of the system. And so for comparison, this system has a thermal resistance that's about 50% lower as compared to the 2014 Honda Accord. So we're predicting better thermal performance than what's currently on the road. And so this is a CAD image of the conceptual dielectric fluid cold plate and the power module that we designed. And so in this case, the lower half is the manifold that distributes the fluid to the 12 jets. And you can see the threaded connections for both the inlet and the outlet. The top part represents the power module, and you can see the 12 devices that are soldered to the top. And so the total volume for this conceptual power module and cold plate is 120 milliliters, and that's half of the 240 milliliters that we estimate is needed to achieve a power density of 100 kilowatts per liter. And so we're meeting the volume requirements. The total flow rate requirement is 4.1 liters per minute, and the computed pressure drop from the inlet to the outlet is about 0.3 psi. And so for comparison, typical WEG-based cooling systems use about at least 10 liters per minute flow rate, and so we are requiring lower than that. And the pumping power, which is the flow rate times the pressure drop, is about 80% lower as compared to the 2014 Honda Accord. So we're predicting better thermal performance at a lower pumping power. And so this slide describes the flow path within the cold plate. And so we're using a parallel flow configuration that's shown by the blue line there. And so the fluid comes into the inlet, and then it flows through a manifold, and then it's distributed to the 12 jets that are directly below each device. The spent fluid then exits out the opposite end. And so we did a lot of work to design the internal channels to both minimize the pressure drop and to also evenly distribute the fluid to the 12 devices. And the flow distribution is shown on the right. So on the right, each bar represents the flow rate for each jet. And so in this case, we're predicting a flow variation of about plus or minus 5%, which is relatively minor. And the effect of that variation on the temperature is shown on this slide here. And so here I'm showing the temperatures for the 12 silicon carbide devices. And so this is from the inverter scale conjugate heat transfer CFD model. So essentially we're modeling the entire, the 12 devices in the cold plate. And so the model included or resolved to the fins that were a couple of millimeters or very small. And so it required very fine meshes with over 100 million elements. And so this work was done in our supercomputing cluster here at NREL. And so in this case, we imposed 2.2 kilowatts of heat that was evenly distributed through 12 devices. That resulted in a device heat flux of about 718 watts per centimeter squared. We used alpha 6 fluid at a total flow rate of 4.1 liters per minute and an inlet temperature of 65 degrees C. And so essentially the fluid comes in from the top right-hand side. It impinges on the fins that are directly behind the devices. And so the results are summarized on the table below. And so this inverter scale model predicts a maximum junction temperature of 222 degrees C. And that's consistent with our prior device scale models, which predicted about 220 degrees. We are predicting a temperature variation between devices of about 2 degrees, and we attribute that to the variations in the fluid flow rate that I talked about on the prior slide. The estimated pressure drop from the inlet to the outlet is about 2,200 pascals, and so that combined with the flow rate gives us a pumping power of about 0.16 watts, which, as I mentioned before, is about 80% lower as compared to the Honda Accord hybrid system. And so then this system achieves a volumetric thermal resistance of about 8.7 centimeters cubed degrees per watt. And so we are exceeding the volumetric thermal resistance target of 21 centimeters cubed degrees per watt. In other words, lower resistance is better. And so based on the fact that we have passed that resistance, we estimate that a cooling system like this could potentially enable achieving the power density of 100 kilowatts per liter. Now, in this case, we're only looking at the thermal aspects. There are electrical and mechanical aspects that have not been considered at this point. But from a thermal perspective, dielectric fluids have the potential to allow for very compact packaging. And so the next slides that I'm going to be showing describe our experimental work. So we've done a lot of work to design and fabricate components to conduct the experiments. And so in this case, we're going to be using resistance heaters to simulate the silicon carbide devices. And so the challenge with this is that we're trying to design a system that can dissipate over 700 watts per centimeter squared and operate at very high temperatures. And so we created this custom system that used cartridge heaters that were embedded within a copper block. And the base of the copper block had these 4 legs, and each leg had a footprint of about 5 by 5 millimeters, which is equal to the footprint of the silicon carbide devices that we're simulating. And so each of these legs represents a silicon carbide device. And so for the experiments, we're going to be using 3 of these copper blocks to represent the 12 devices. And so within each leg, we are embedding 2 thermocouples to measure the temperatures and then also to compute the heat fluxes through each of these legs. And so on the left, you see the temperature contours from the FEA. And this is for the 718 watt per centimeter squared heat flux condition. And so we are predicting very high temperatures on the cartridge heaters, but they are within the vendor stated limits. The temperatures at the base of the copper block, which is the part that simulates the silicon carbide devices, is about 210 degrees, which is consistent with all of our other modeling work. And so we've also completed the cold plate fabrication. The one that I'm showing here was 3D printed using nylon. So we have since 3D printed these using polycarbonate, and we're actually going to be using polycarbonate material as for the actual experiments, and that's because it can operate at higher temperatures. It's a little bit stronger. And so we use 3D printing here because it's a convenient way of fabricating and testing prototypes, but the actual design itself does not need to be 3D printed. It could be made using other manufacturing techniques, including injection molding, casting process. And then the picture on the right just compares the size of the cold plate with that of a typical cell phone. And the intent here is to show how compact the overall system is. And so this is a picture of the dielectric fluid loop that we fabricated to conduct the experiments. You can see the cold plate in the background. The dielectric fluid is stored within the stainless steel reservoir that you see on the back. Within the reservoir, we have a heat exchanger coil that we circulate silicon oil, and that's how we control the temperature of the dielectric fluid during the experiments. And so then we use a gear pump to circulate the fluid. The pump pulls the fluid from the bottom of the reservoir. It circulates it first through a flow meter, and then it goes through the heat exchanger, and then it drains back to the reservoir. And so during the experiments, we're going to be measuring the temperatures of the 12 heaters. We're also going to be measuring the inlet and the outlet temperature. And then we also have a pressure transducer that we use to measure the pressure drop across the device. And so we're going to be using this to validate the modeling results that we've obtained. And we're going to be looking at the effects of the flow rate. We want to conduct tests up to about 4 liters per minute. We'll probably take it up a little bit higher than that, maybe 5 liters per minute, just to see the effects. We also want to look at the effect of fluid temperature. So we want to look at temperatures from minus 40 degrees C, which can simulate the very cold winter condition somewhere, up to 70 degrees C. And then we're also going to be looking at different dielectric fluids. We're currently conducting tests with Alpha 6. We're also going to conduct tests with AC100, and we also plan to do tests with ATF as the coolant. And so we've also done some work to model the short circuit behavior of the cooling concept. And so it's well known that the short circuit withstand time of silicon carbide MOSFETs is lower than that of silicon IGBTs. And so what we're trying to do here is to see if the current cooling concept has any effect in delaying the temperature rise during a short circuit fault condition. And so we developed this one-dimensional transient thermal model that you see on the left. And so the model is essentially a sliver of a device. It includes all the micrometer layers within the silicon carbide MOSFET. We use temperature-dependent properties for the different layers, and we apply the volumetric heat load at the junction. And so the results are shown on the right-hand side. I'm showing the temperature versus the time response. And note that the time is in microseconds. And so the red line represents the performance for a conventional silicon carbide device with only a 5 micrometer metallization on the top side. So that's essentially the source pad metallization. And under the short circuit condition that we modeled here, this configuration had the highest temperature rise. The blue line represents the temperature response for the current design, where we have soldered a heat spreader to the top of the device, and then we're applying a heat transfer coefficient on top of that heat spreader to simulate cooling from the dielectric fluid. And so what our results show is that the current cooling strategy really has minimal effect in delaying the temperature rise at these microsecond timescales. We are predicting slightly lower temperatures for the current design, but the results are fairly negligible. And likely, in reality, delaying the temperature rise during a short circuit fault condition would likely require modifications within the device, and changing the package around the device likely has minimal effects, as we are seeing here. But it was a good experiment just to see what the effect of this cooling strategy would be on the short circuit fault condition. And so the second half of my presentation is related to gallium oxide device research. And so this work was led by Shrikant Naramanchi, who is our team manager. This slide shows why there is interest in gallium oxide semiconductors. And so currently most of the power electronics are made out of silicon, and that's because this is more a mature technology, cost is low. With wide bandgap semiconductors, including silicon carbide and gallium nitride, have better performance, but at a higher cost. At this point, I think only the Tesla Model 3 uses silicon carbide MOSFETs. That'll probably change going forward as the cost of these wide bandgap devices comes down. But gallium oxide offers the promise to achieve the performance of silicon carbide and gallium nitride at the cost of silicon. And so there's a lot of interest right now in developing functional gallium oxide devices, and that was one of the objectives for this project. And so the spider chart below compares the performance of gallium oxide with that of silicon, silicon carbide, and gallium nitride. And as you can see, gallium oxide has the highest figure of merit. It has a low cost, but its one drawback, or one of its drawbacks, is its thermal conductivity, which is relatively low. And so this slide highlights one of the main disadvantages of gallium oxide, which is its low thermal conductivity. And so on the graph here, I am plotting the thermal conductivity versus the temperature. And so this data was taken from that first reference there from Wong et al. So gallium oxide has an anisotropic thermal conductivity. The thermal conductivity in the true plane direction is shown by the red line, and that's about 40% higher than the thermal conductivity in the in-plane direction, which is shown by the blue line. And so when compared at the same temperature of 150 degrees C, gallium oxide has a thermal conductivity that's about 84% lower than silicon and about 93% lower than silicon carbide. And so it's this low thermal conductivity that makes it more difficult to remove the heat from these devices. And so one of the objectives for this project was to develop thermal management strategies for gallium oxide-based power modules. And through modeling, we showed that the dielectric cooling concept that I talked about is a promising way of cooling these devices. And the reason for that is because we are cooling the top side of the device, which is near where the heat is being generated. And so instead of conducting the heat through the device, we just directly move it from the top side. And that ends up being a very effective method of cooling these devices. And so this slide shows the results of a techno-economic analysis to compute the cost of a gallium oxide wafer, and then to compare its cost with that of a silicon carbide. And so models were used to estimate the cost for various processes that are involved in the wafer fabrication process. And so the cost breakdown is shown in the pie chart on the left. The chart on the right shows the cost of silicon carbide and gallium oxide. And the main takeaway from this is that they are predicting that gallium oxide wafer cost can be anywhere between 3 to 5 times lower than that of silicon carbide, which can result in about 2 to 4 times cheaper devices. And so there seems to be a path towards decreasing that cost. And so this work was published in the journal Joule, which I referenced there if you have interest in that. And the next 2 slides discuss the device electrical modeling work. And so the focus here was to design functional gallium oxide devices. And so TCAD, finite element modeling, was conducted using Centaurus Synopsys software. And so various device architectures were modeled to understand their electrical performance. Below are 2 designs, and I believe both of these were modeled. The vertical FinFET design on the right provided some promising results, which I'll talk about on the next slide. And so these are the modeling results for the gallium oxide vertical FinFET design. This work was actually done by Ram Kotecha in our group, and he published a paper on the Journal of Solid State Science and Technology. And so on the top there, I'm showing the current voltage characteristics for room temperature in the middle, and then with self-heating effects on the right. And on the bottom, I have the capacitance voltage characteristics, and then the device short circuit characteristics on the bottom right-hand side. And so these preliminary results show good transistor performance is expected from vertical FinFET devices. And so in conclusion, we have completed the design of an inverter-scale dielectric fluid concept that is predicted to enable achieving a power density of 100 kilowatts per liter. We have fabricated a cooling system prototype and a dielectric fluid flow loop, and are working to conduct experimental demonstration of the cooling concept, and that work is in progress. We're also conducting research to develop the next generation ultra-wide bandgap gallium oxide devices, and the device modeling shows that a vertical FinFET architecture can give promising device performance. Before I end my presentation, I just wanted to give a quick overview of our group's portfolio of projects. So in my presentation, I talked about 2 different projects. One was a DOE VTO funded. The other one was an NREL LVRD funded project. But we also have conduct research for other agencies. We currently have 2 AMO Power America projects that we're working on, and we're also have projects that are funded by the Department of Defense and various industry-funded projects. And then finally, I just want to give an overview of our lab's thermal management capabilities. So we have a variety of experimental flow loops. We have various single-phase liquid cooling loops that we can use to test water ethylene glycol. Some are dedicated for automatic transmission fluid. We just made one for dielectric fluids. We have various 2-phase coolant loops that we can use to test both low and high pressure refrigerants. And then we have an air cooling test bench, T3 stir, and various equipment to measure the thermal properties of materials. In addition to that, we have extensive modeling capabilities. And then finally, just summarizing some of our thermomechanical reliability capabilities. Those capabilities span from the synthesis of bonded interfaces to accelerated testing of those components, non-destructive imaging and evaluation, and then we can also couple some of that experimental work with thermomechanical modeling to develop lifetime prediction models. And so with that, I'd like to conclude the presentation, wanting to acknowledge the funding sources there on the top, and also the team members that contributed to this work. And so, yeah, with that, I guess I can answer any questions.
Oh, thanks very much, Gilbert. That was a very comprehensive treatment of the topic. I really appreciate it. And also, personally, it's great to see a mechanical engineering focused presentation for the first time.
Okay, that's great.
Are there any questions? I don't see any. There's only one question in the chat window, so please use the chat function to type in any questions you have. The first question is, are there any concerns with the alpha 6 dielectric fluids flash point being so close to the critical junction temperature of the device?
Yeah, that's a very good question. So actually, the junction temperature that we're predicting in this case is about 222 degrees C. And that's at the junction. The temperatures that the fluid is exposed to are closer to about 200, if not lower than that. So we have a pretty good a delta T there between the contact temperature and the flash point. Another thing is that these are closed systems without any oxygen or with minimal oxygen, and so the potential of flashing is fairly minimal. Again, this is an R&D project, and so we will plan to look at those aspects, but we feel we're well below that to prevent the flash potential.
Okay, thank you. Are there any more questions? Any questions before we wrap up for the day? Again, everyone is muted, so if you have a question, you need to use the chat function of WebEx. It should be in the upper right-hand corner of the toolbar, and you type in your question, and then I'll read them out. Okay, hearing none, we'll wrap up for the day. Again, thank you very much, Gilbert. That was a very good presentation. I look forward to getting the slides from you for anyone who requests them. And thank you, everyone, for joining us, and we'll see you a month from now on Wednesday, December 4th at 12 noon.
Okay, thank you, Rogelio.
You're welcome.
And thanks to everyone for listening in.
Bye-bye. Bye.